It's question show time. Your questions, my answers, as always, wherever you are, across my channel. Question pops into your brain, write it down, I'll gather them up, and I will answer them here. Dustman, I wondered what would happen if a star went supernova right next to a black hole. All right, so let's imagine this scenario. You've got a really giant star, maybe something with 20 times the mass of the sun, 30 times the mass of the sun, and it is orbiting a black hole. And the black hole is going to have 15 times the mass of the sun, 25 times the mass of the sun, some large amount. And the two stars are orbiting around each other, because that's the only way you can have a star and a black hole be really close to each other, is if they're in some kind of binary relationship. And so maybe their masses are roughly equivalent, but even if they're not, then the star is orbiting the black hole, or the black hole is orbiting the star, whoever has the most mass. And so then the first star went supernova a long time ago, and now the second star goes supernova. And when that second star goes supernova, before you had this anchor, you had these two objects that were orbiting around each other, and now one has disappeared. The mass has gone away. Now, in some kinds of supernova explosions, if the star is big enough, like 50 times, 60 times the mass of the sun, then when the star goes off as a supernova, it's gone. There's no remnant left behind. It is just a puff of star, and it's gone. And so now there's no gravitational anchor that's holding onto the black hole, and it's free to just go careen off in a direct line. If it has enough velocity, it could get kicked out of the Milky Way entirely. If the star that the black hole is orbiting together with is maybe a little bit smaller and it turns into a black hole, well, then they're still going to be orbiting around each other. Or if it's even less massive and it turns into a neutron star, they're still going to be orbiting around each other, just in a different configuration depending on the amount of mass that they had. Now, I'm sure you're wondering, like, what would the explosion of a supernova do if it was right next to a black hole? Well, the black hole is perfectly able to gobble it all up. So all of the energy that actually crosses the black hole event horizon goes in. All of the matter, all of the debris, all of the fragments, they all just go into the black hole and they get added to the mass of the black hole. And so the black hole gets a little bit more massive, not a lot, because the amount of that star that's actually going to hit it. And then any debris that's sort of sitting around, and as the black hole is careening through this debris field, it's going to be gobbling that up, maybe turn that into an accretion disk around it, and then eat all that as well. So it's not going to do any damage to the black hole. You literally cannot do damage to a black hole. Anything you try to do just makes it stronger. But if the binary companion disappears because of its supernova, then the black hole is now unleashed into a random direction to fling through the Milky Way. Eka A. My thought on alien civilizations is star travel is very hard. Too much debris between stars wears out ship hulls, if not smashes them to bits. I expect multicellular life evolves in many places, however, it usually takes too long for highly complex multicellular life like us to evolve on most planets, and a certain level of environmental hostility is needed for it to evolve. Well, I want to tackle the first part here, where you said that it is probably too hard for spacecraft to be able to travel. Now, it's really important to make this distinction. Is it really hard, or is it completely impossible? Because if it's really hard, it'll still happen. It'll just take a little bit longer. And in the vast scale of the age of the universe, just a little bit longer, there's plenty of time. So let's say instead of being able to travel at 10% the speed of light, because you want to be really careful, you only travel at 1% the speed of light. So instead of it taking you 1.5 million years to completely settle the entire Milky Way, it takes you 15 million years. But take 150 million years to do it. It still is going to happen over that time frame. But if it's completely impossible, there is no way that it can be done. Even though we have examples of interstellar meteorites, we have interstellar comets passing through the solar system, so we know rocks can do it. But if it's completely impossible, then that means that we will never do it. So either it's possible, and then we're going to do it, and then we're going to settle the entire Milky Way, or it's utterly impossible, and no matter what we do, no matter what we think of, no matter how hard we try, from now until the end of the universe, we will never think of a way to do it. It doesn't seem realistic to me. Now, back to this idea of multicellular life. it feels to me like once you get to multicellular life, then it's just a matter of time before some level of intelligence forms. But we don't know. We only have one example of life in the entire universe that we know of. And so until we can find another example of life to compare what happened here on Earth with there, we'll never know for sure. Matt Higgs. I notice in a lot of videos you stress that it's impossible to fly at the speed of light, which I understand is true with our current knowledge of physics. But over 100 years ago, some of the smartest people in the world were saying air travel was impossible. Any chance are the smartest scientists today wrong? Thanks as always for your great content. I think it's important to make this distinction between a thing that we know is possible, but we just can't do it yet, to a thing that we think, according to the laws of physics, are completely impossible. So to use your analogy of air travel, we have birds, there are bats. We know that flight, powered flight, is a thing that is possible, and evolution figured it out. And there were some great comments actually in the section where you posted your questions, so people were talking about this as well, that we knew that there was some way to fly. We just didn't know how. And there were some people that said, oh, well, it's going to be impossible. But then there was people like the Wright brothers, and there was probably hundreds of teams working, looking at a bird and going, okay, if a bird can do it, we can do it. If a rock can fly from another solar system to us, we can do it. Now, when we think about going faster than the speed of light, no matter where we look in the entire universe, we don't see anything going faster than the speed of light. We see quasars, the actively feeding centers of supermassive black holes with churning material, which have these enormous jets of material that are blasting out into space. And they just happen to be going at the maximum speeds predicted by relativity. They're going very fast. They're going at relativistic speeds, but they're not exceeding the speed of light. And there is nothing stronger, more powerful in this universe than a spinning black hole at the middle of a galaxy, and yet they can't do it. So the analogy I don't think holds. We don't look out into the universe and see things moving faster than the speed of light, and so that holds with our expectation of physics say that you can't move faster than the speed of light. Are we wrong? Probably, maybe, who knows? We'll find out. And if we do find out, and we find out, oh, it turns out that when we just look in a different spectrum in the universe, then suddenly we see everybody moving faster than the speed of light, and then everything changes. Sometimes that happens, and sometimes it doesn't. But we can't make any predictions about the physics that we don't understand, because if we could, then we would understand it to some degree. Might as well just be magic. Mike McHugh. How does the Mars helicopter find its way since there's no GPS? One of the coolest things with the Perseverance rover is that it's going to be equipped with a tiny little quadcopter. Actually, it's like a little drone with two rotors that go in opposite directions. And the speed of the rotors turning and the low gravity on Mars and the density of the atmosphere is just enough for this thing to be able to fly around. And so Perseverance, when it lands on Mars, it's going to extract this tiny little helicopter, place it on the ground, move away, and then this thing is going to start flying around on Mars. It's going to fly, it's going to land, it's going to power up its solar panels again, it's going to fly some more, and it's going to be taking a bunch of images of the surroundings. How is it going to navigate? It's not going to go very far, and it's not going to be very sophisticated, and it's probably not going to make a lot of flights, but it will be equipped with a tiny little camera. It's going to be able to take pictures, and it's going to be able to do some basic hazard avoidance as it's flying around. And then it's going to land, it's going to transmit its data to the Perseverance rover, and it's going to do another little flight a couple of days later, and over time, and then eventually, it's just inevitable, the thing's going to crash. I mean, who hasn't crashed a drone? So don't assume that this thing is going to work for a long time, but it's going to be pretty exciting to have this thing flying around Perseverance, taking images in the area. Mads Hogg Sorensen. Wait, so if Boeing costs $90 million and SpaceX seats cost $55 million, why would NASA ever buy Boeing seats? One of the great things about the new NASA crewed program is that when they set upon this journey, they chose two providers. They actually chose a bunch, but for the actual capsules, they chose Boeing with the Starliner, and they chose SpaceX with the Crew Dragon. And they negotiated separate deals with both of them. And the idea here is that if one of these capsules maybe has more trouble getting off the ground, maybe it has some issues, you can still fly with the other one, and you've got redundancy. And so SpaceX is providing it at 55 million. Boeing is going to be providing it at 90 million. Both still give the United States the ability to launch astronauts to the International Space Station. Both are way cheaper than it costs to launch things on the space shuttle. Both are competitive with what it costs to pay the Russians to be able to fly on board Soyuz, and yet they all launch from American soil. So that was the deal that NASA struck with these two providers. Maybe down in the future, if Boeing just can't get the rockets launching, can't get the Starliner working the way it needs to, then maybe they won't go with them. But maybe Blue Origin will step up and have a capsule capable of carrying people to the International Space Station. I think it was a really clever idea to have this redundancy. And so if one provider doesn't work out, you use the other one, back and forth between the two. And you've always got this competition, and Boeing knows that they've got to try to bring their prices down to be more like SpaceX. We know that competition is always a good thing, especially when it comes to large government projects like this. So I think it was a great idea. One of the smartest things that's come out of NASA in a long time. I love it. Stew mass. I'm trying to get my head around how different parts of the universe can exist in different times simultaneously. Surely the whole universe must exist in the same present moment. Otherwise, how can objects in the past interact with objects in the future? This is not semantics or wordplay. I just can't see the logic. Can anyone explain, please? One of the implications of relativity is that we experience the passage of time differently depending on the speed that we're moving relative to each other, as well as the relative gravity well that we're existing inside. So here on the surface of the Earth, we're experiencing a different passage of time than somebody who is out in the middle of space, orbiting between Earth and Mars. Somebody who is orbiting around the Earth is experiencing a different passage of time because they're moving than somebody who is standing stationary on the surface of the Earth. And you are experiencing some balance of gravity well and velocity compared to other people, no matter where you go in the universe. And this number can actually be pretty big. We did a calculation quite a while ago that if you're on opposite sides of the observable universe, you've experienced about 30,000 years different amounts of time than some other observer in another location. And so, yeah, you can imagine, like, whoa, everybody experiences different amounts of time, man. That's so weird. And I know it seems really bizarre to think, well, like, if you're on the surface of a planet orbiting around a supermassive black hole, you experience a couple of hours, but other people have experienced 30 years. That's just so weird. And yeah, it's weird, and that's how the universe works. Now, I can imagine, like how do things exist? They just experience different amount of time. They age at different rates. And when you think about the movie Interstellar as sort of that classic example, right? They went down to that world, orbiting the supermassive black hole. They hung around, watched this big tidal wave pass through, and then when they got off the planet, everyone else had experienced decades of time, and they just experienced different rates of speed. And it would be like watching somebody, but you're watching them moving in fast forward, or you're watching them move in slow motion, but yet you're still in the same universe. I know it's a really troubling idea, and yet that is the foundation of the idea of relativity, that the thing that must remain certain is the speed of light in a vacuum. No matter where you are, you must always be seeing the speed of light, moving at the speed of light. And if your time needs to change to make that possible, then that's what happens. Guardian 1032. So say we were able to create an Alcubierre drive, a warp drive, etc. Would the same effect on the ship traveling at the speed of light also affect the warp drive ship? Or because it is space-time warping, would it negate the relativistic effects? I.e. when Captain Kirk gets back to Earth, everyone he knows is or is not dead. So we've talked about this idea of relativistic travel is as your speed approaches the speed of light, then you experience dramatically different amounts of time than people who are stationary relative to you. So I hop on my spaceship, I fly to Alpha Centauri, I move really close to the speed of light. For me, the journey only takes a couple of minutes. For you here on Earth, my journey, you watch me go, and it takes 4.5 years for me to get all the way over to Alpha Centauri. I send a message home, I then zip back. Again, I experience only a minute or two, and I get back to Earth. You have watched my spaceship make the entire journey from Alpha Centauri back home. That is relativistic travel. You are moving through space according to the laws of physics. The idea of a warp drive, an Alcubierre drive, is that you are warping space-time itself. And so you are not beholden to the rules of relativity. You are moving space. You are bending, distorting space so that your ship is essentially has no thruster, no drive. I mean, you can have some alternative, but the main job of the drive is to like grab your ship, pull it forward, distorting space-time as much as it needs to, and then depositing you at your destination. From your perspective, you turn on the warp drive and you will be essentially instantaneously arriving at your destination. It's not like Star Trek. Star Trek, it's like you're on some long ocean voyage, but if the real physics of a warp drive would probably, you turn it on and you arrive billions of light years away instantaneously. From our perspective, you disappear and you reappear at your destination. And then and the exact same amount of time will have elapsed for both of us. And then you will hop in your spaceship, you'll come back, and you will not have aged a day, even though you've been billions of light years away. And that's one of the implications of warp drives. Wouldn't that be great if they were real? Here's hoping they will eventually be real, although we have no idea if they ever will. Mariolus 1000. Do you think that China stands a chance at going to Mars in a similar time with the USA? Even though we don't hear much about their space program that much, I think they can pull it off in a similar time as NASA. You're absolutely right. We don't hear a lot about the Chinese space program. We hear occasionally some accomplishments. Sometimes we see stuff on Chinese state media that is, we get to see some pictures. They've done a much better job with their recent moon exploration. They've been releasing pictures more quickly. They've been participating in science journals. But generally, when it comes to their human spaceflight side, it is completely secret. We know that they're building a space station, their own version of the International Space Station, which is going to launch in a couple of years. But beyond that, we don't really know anything. And that is partly because they do a terrible job of just promoting what they're working on. They have to promote all of this stuff into other languages is really hard, into English, into Japanese, into Spanish. And then the other thing is that they're a very secretive development program. And they have no interest in telling us what they're up to in any broad strokes, the way NASA is more beholden to the taxpayers. So China's very serious. They have a new rover that's going to Mars this summer. Now China's going to have a rover on Mars. They already have a rover that went to the far side of the moon. They've had multiple landers on the moon. They have a spacecraft that's orbiting the far side of the moon. They're building an International Space Station. They just launched a brand new rocket capable of launching big payloads that will go to build the space station. They just tested out a brand new capsule that looks very similar to the Crew Dragon. They are learning very quickly about how to build reusable rockets. They've essentially abandoned all other concepts in the long term. They're going after more and more reusable rocketry. Will China get to Mars sooner than the United States? I don't think so, because SpaceX, Starship, Elon Musk, that's the plan. But I wouldn't rule it out. And it definitely would be within a decade or two of what happens in the US, which is pretty close in space exploration terms. I have really come to the realization that my understanding of what's happening with China as one of the dominant participants in space exploration is totally lacking. And so some of you learn, I'm learning Chinese. I practice Chinese 3 or 4 hours a day, reading, practicing listening. I'm starting to read scientific articles in Chinese. I practice with people every day. I am so fascinated by what they're up to that I have actually made a serious commitment to upgrading my ability as a science journalist to be able to just understand what is going to be making at least half of the space exploration news in the coming decades. And so hopefully I'll be able to pull this off. It's very hard, but I think you should not rule out what China is up to. They're very capable, they're very committed, they have a lot of budget, they don't have a lot of internal arguments that I can see from the outside on what they're up to. They're taking this very seriously. Engineering, scientific discovery is very important in the society. Scientists, engineers are preferred professions for people to go into. Yeah, I think anyone interested in spaceflight should take the actions of China very seriously. Liverpool 0690. How come we're not tidally locked to the sun? Tidal locking is this situation that happens when, say, the moon and the Earth interact with each other, and the moon gets squished by the Earth through its gravity, and then sort of flattened a bit. And then this flattening provides Earth's gravity with handles. And then as the moon is turning, Earth is torquing on these handles and slowing down that rotation. And as that happens, the distance between the Earth and the moon change. And over some period of time early on in the moon's history, the Earth was able to slow down the moon's rotation until, from our perspective, the moon always shows the exact same face to the Earth. The same thing has happened with Jupiter and the large Jovian moons. The same thing has happened with Saturn and some of its large moons. And in theory, we would see the same situation in, say, the TRAPPIST system, where you've got a red dwarf star, you've got all these planets orbiting around it, they're very close to the star, they will get tidally locked. So they only show one face to the star at all times. And in theory, this could happen in our solar system as well. Mercury, much closer to the sun, over long periods of time, would get slowed down to the point that it's always showing the same face, or Venus, or Earth, or whatever. But the thing is that, one, the distances of the planets is a lot greater. Like, you're looking at tens of millions of kilometers, not a very tight orbit. And the second thing is you've got the interactions of all these other worlds. You've got Jupiter, you've got Saturn, you've got all of the other planets, and their gravity is pulling and pushing and tugging and tweaking and changing everything. And so things can't stabilize down into one tidally locked orbit. Denarm 52. Is there a possibility that we can't find dark matter, dark energy, or the missing antimatter because they exist in the dimensions that string theory posits, which we are unable to perceive? I'm not an expert in string theory, but as I understand, string theory suggests that there are more dimensions than the 3 spatial dimensions that we experience. They're just coiled up really tightly, and if you could get really close, you could experience them very, very small levels, and that maybe these things, dark matter, dark energy, are somehow leaking into our universe from those other dimensions. Maybe. The thing is that we can detect dark matter. We don't know what particle exactly is causing it, but there are probably close to a dozen independent tests which have measured dark matter out there in the universe, its scale, its size, its location, its density, where it's distributed, close and far, galaxies that have it, galaxies that don't, clumps that are only dark matter, etc. So dark energy is a little trickier, but I don't think we've gotten to the point where we need to kind of go, okay, we're absolutely certain that there is nothing in this universe that is causing these things. Maybe there's other universes. There's still lots of room to look in this universe before we give up. Controlled chaos. Fraser, hypothetical question for you. Amateur astronomers discovered an interstellar asteroid that will fly through our solar system in the next 5 years. We map its trajectory and see that in 100 years, it will also fly by another star. Could we hitch a ride on it to get us to another star? So here's the problem. If you could safely hitch a ride on an asteroid, then you wouldn't need to hitch a ride on an asteroid. I'll explain this, what I mean by this. So imagine you're standing at the side of a freeway and there's cars driving really quickly past you. And if you could jump in front of one of the cars and hitch a ride with that car, then you could go to wherever that car is going. Of course, you would want that car to slow down first. And let's say the cars aren't going to slow down. Then you would need to be in a car that is going the same speed as one of these cars that you want to hitch a ride to. And if you can be on this car that's going the same speed, then you don't need that car because you've got your own car that's going the same speed. In order for us to be able to hitch a ride on an asteroid, we have to match velocity precisely with it. We have to have a giant rocket capable of moving our spacecraft in exactly the same velocity as this interstellar asteroid. And if we can do that, then our spacecraft is going to follow the exact same trajectory that this asteroid is going to follow all the way to this near star system. So in terms of like a pure energy saving, there's no value to be able to do that because there's no friction in space. Once you get up to the speed of the asteroid, you're going to go to the same destination the asteroid's going to go to, and there's no energy saved. That said, the one thing that would be of value is raw material. So say you send a factory spacecraft to match trajectory with the asteroid, it lands on the asteroid and then digs in and then starts turning the asteroid into stuff that the spacecraft needs. Now you're kind of like living off this life raft while you're going. And I think there's value in that, for sure. In addition to just the scientific analysis that you could do of the asteroid, you could imagine some colony ship, some starship gets launched with 100 people on board, with a bunch of factories and stuff on board. And then an asteroid comes flying through the solar system, and we know that it's going towards some other star system. And then our starship matches velocity with the asteroid, docks with the asteroid, the settlers get out, and then they start building cities inside the asteroid while the asteroid is moving to another star system. That's kind of cool. But apart from that, there's no value in just trying to jump on board an asteroid. If you can do that, then you don't need it. Matt P. I want to see a video of some scientists turning energy into matter. If you could do that, you could make any object you wanted with a powerful enough laser and a computer and an AI program. I will show you a video of scientists turning energy into matter right now. It's called a particle accelerator. So what's actually happening when you think about a particle accelerator, think about, say, the Large Hadron Collider. What you've got is you've got these two streams of protons that are accelerated around this gigantic ring using electricity to go faster and faster and faster until they are approaching almost the speed of light. And then, so that each individual proton has both its mass, but also an enormous amount of kinetic energy. And then these protons are smashed together at where the beams cross. And as these particles are smashing into each other, all of the energy, all that kinetic energy that is part of their movement is now in this incredibly dense area. And if you get too much energy in this incredibly dense area, it has to freeze out as particles. And so you get particles appearing out of the energy that was trapped or that was built up in the kinetic energy of these particles that are moving around. And that's all a particle accelerator is. That's how scientists discover new particles, is they smash particles together, and the new particles that come out were created because the energy was so dense in this tightly packed little area, which is kind of an amazing idea. So if you were to build some kind of replication system, you would need to have a particle accelerator that was accelerating particles and then smashing them together right in front of you in a way that produced the right atoms for your cup of coffee or your tea Earl Grey hot. So what you don't see in Star Trek is the gigantic particle accelerator that is accelerating all the particles to make the replicator work. All right, awesome. Once again, thank you everybody for sending in your questions. I love this. So keep them coming. Whenever there's a show, if you have some question pops into your brain, write it down. I'll gather them up and I'll answer them here, and I'll see you next week.